Sorry. So this is the experience you have when working with real hardware. And it kind of reminds me a tiny bit on also working with some neuromorphic devices. Sometimes they work, sometimes they don't. But from my experience, there's usually a good cause for why they work and why they not work. And I'm talking about experiments on brain scales. And these are experiments that did work. So what is brain scales? Brain scales is this. So this is our machine room in Heidelberg with the 20 wafer modules. And what you see here is that there are 4 modules per rack connected with a lot of Ethernet cables and a control cluster in the middle. So now we're going to make a journey like from the outside to the inside and then back again to the experiments. Okay, so what you see is one of these 20 wafer modules, and it contains a 20 centimeter wafer processed in a 100 nanometer CMOS project. And this is connected to a main PCB, which is then in turn connected to 48 FPGAs, some power supplies, auxiliary boards for analog readout, and all these components you see laid out on this table below. And they all make up for one of our 20 wafer modules. And this system is now in development for over 10 years. And at the heart of it, there is an analog neuron circuit. So you heard a lot about digital implementations of neuromorphic device, and this here is a part analog implementation. So you see in the upper part a layout drawing of 2 neurons, 150 times 20 micrometer in size, and they model the adaptive exponential integrate and fire model. So when you have an analog implementation of a neuron, you need dedicated circuits for resting potential, reset potential, threshold potential, and so on and so forth. So there is no multiplexing. Every neuron we have on the chip, on the system, does need to have these dedicated circuits. So why go through all that hassle? For me, it is the accelerated dynamics that come from doing this approach, and especially in this substrate, the CMOS substrate. So when you just think of a simple RC circuit and look at the time constant of it, then it's just a multiplicative of C and R. But both C and R are very small on CMOS. So what you get is a very small time constant. And when you compare the time constants we have on our system to that of biology, you get a factor of 10,000. So the dynamics that these neuron circuits emulate are accelerated by a factor of 10,000. So then we have a neuron. So far so good, but of course we need more than one neuron. We need a couple of neurons. And on one chip, we have about 512 neurons. And what's the larger share is the number of synapses, over 100,000 plastic synapses. So the neurons and the synapses are both analog and thereby accelerated. And of course, these neurons can spike. But the spike is intrinsically a digital value, and these are then transmitted digitally on the chip. So we have a mixed signal system, analog neurons and digital communication. And then one of these spikes will travel through the chip. There are a lot of tiny switches you can set. So for example, here is a switch that you can set in the crossbar array, and you route these digital events. To configure the neurons, you need, again, some kind of analog parameter storage. We do this in floating gates. And now you have one chip with your neurons and your synapses. But of course, scaling, as Chris told you, is very important. So we do not only want to have one chip, we want to have many chips, and as many as you can get on one wafer. So we take the wafer, do not cut it, and IZM in Berlin will apply a post-processing layer, a redistribution layer on top of it that allows for wafer scale networks. So let's do this journey again from the inner to the outer. We start in the middle of the synapse array, and these structures you see are the size of the features in the process, so 180 nanometers. And we now go outside, and you will see repeating structures, and this will be the synapses that you see. So now you see all this squarish kind of objects, and by now some larger structures. You see some pads for connection or some power distribution. And now you can start to see a single chip, but we are not there yet, so we zoom out more and more, and at the end we will see the wafer. And all these chips can talk to each other, so every neuron can fire and send its spike to some other neuron on the wafer. So now that we are hypnotized enough, I have to tell you that there is unfortunately, of course, no free lunch. So these analog components are great, they are fast, we can make them, we can scale them, but alas, we have to configure them. And that is because when you do an analog approach, every mismatch from transistor to transistor can matter. So it will change the properties of your circuit. And what you see in the left plot here is calibration curves for the synaptic time constant. And on the x-axis you have your programming parameter, it's a digital programming parameter, and you see in the different colors responses from different neurons. And you see that they have a different synaptic time constant for the very same value of your digital parameter. So what you need to do is, of course, you measure the curve for every neuron, and you fit it, and then you have a lookup table from your desired synaptic time constant to your target time constant. But sometimes this is not enough, because you will see that some neurons cannot have a very low synaptic time constant. So it's not that you just once calibrate and then everything is done. You still will have to live with limited parameter ranges for some of them. But when you have all done that, you have your calibration for the parameters that are important to you. You still need to now configure the system. And we also already heard that twiddling with the bits is fun, of course, but maybe you don't want to do it on a regular basis. What you really want is you want to describe your networks in a high-level abstraction. And from the predecessor project of the Human Brain Project, the Pine language was developed. And Pine is a network description language, which is to a certain extent independent from the backend. So that means that programs you describe can be run on different platforms. For example, Spinnaker or Brainscales, or hopefully Luigi in the future. So what you do is you simply instantiate in Python, for example, a stimulus, a population of neurons, and then a projection between the two. You connect the stimulus to your neuron. And that is basically enough for the backend to extract the necessary bits you need to write on the hardware. And when we do that here on the right side for a bit of more complicated stimulus, you see the comparison of the Brainscales neuron response to a simulation. And you see that it's a fairly good agreement. So in this first part, it looks really good. Then here, the simulation shows a bit more inhibitory. And then when you mix the two, of course, you also get some disturbances. So you could then go back and try to calibrate more, but maybe you are out of students, so you have to live what the state is. And in addition, we don't really want to calibrate to the last %. At the end, the networks should learn by themselves or be robust against these fluctuations. So as soon as there is a fair agreement, I would always say go on, solve the next problem that there is. So one problem, for example, is the backend. And in our case, it's a rather complicated machinery. So you define your network abstract, you write it in Pine, and then you need to do something that we call mapping and transformation, which is take this abstract description and do all the necessary steps you need to do to really run it on the hardware, on the substrate. So you need to place your individual neurons, you need to route the spikes, you need to record the spikes, and then you need to talk to the FPGAs to load the input spikes and run the network. So this we all have now, and we can start to go to the experiments. And for one of the first experiments, we choose just to classify MNIST with a simple feed-forward network. This does not mean that this kind of network is the best suited for the platform. It's just some task that has a clearly defined figure of merit, the accuracy, and it's easy to understand both from the machine learning point of view, but also from the point of view what's going then on the hardware once it works. And it's also quite small, so only a couple hundred neurons and a couple of thousand synapses. So, but when we want to map this network on the hardware, we face a problem of, well, how to do it, yeah. What do we want to really mean by having this feed-forward network? So what we did is we trained it on an artificial neural network, just with ReLU units, and then we did a simple transformation of the weights to the hardware weights, and we equate the output of the ReLU unit to the rate of the individual neurons of the spiking neural network. And when we did that, we saw that it worked fairly well, so you get a 70% accuracy. The artificial neural network would be much higher. And this is not surprising because you have many different factors in there. You have the fact that a spiking neural network is not an artificial neural network, and you have the fact that you still have some leftovers, some systematic deviations due to imperfect calibration. And also you have try-to-try variations because this floating gate storage is programmed once per experiment, but it has some statistical fluctuations. So you get a distribution of synaptic weights, for example. And what we did then is we continued the training of the artificial neural network, but now again replacing somehow the backend. So what we did is we take the MNIST data, put it into brain scales, extract the spikes, go back to the ReLU activity, and do the classical backpropagation on the host PC. Do a weight update, do the weight discretization, and continue this hardware in the loop. And by this, we can recover the classification accuracy and do not care about all the differences between the artificial neural network, the missing calibration, and the statistical fluctuations from the try-to-try variations of our floating gate memory. And then you can also check the raster plot. So here the time goes up and the neurons go to the right. And you have the different classes, the two hidden layers and the label layer. And you see that the correct label neuron spikes predominantly when the class is given. Here the time is given in seconds. But again, this is the biological unit. You have to divide it by 10,000. So when we present one digit for 1 second, it's really only the 10 seconds of it on the clock on your wall. So you get a very fast response to your classification. So this only works if the floating gate memory is stable. If it would decay over time, you could not do this loop. So we did an experiment on how stable this storage is. And we tracked the classification accuracy over days. And even after about 2 weeks, the classification accuracy did not degrade. And by this, we can say that when you once program your system, you can start to change the weights and really continue this learning also over a longer period of time. So this was one class of experiments we do. Another one is solving constraint satisfaction problems. And also here we started with a simplified version of Sudoku, so a children's Sudoku, because also our system is young. So we have 4 times 4 Sudoku. And the question is how to solve these constraint satisfaction problems. And you can do this with simple winner-take-all-like structures, where each rule of the Sudoku is implemented as one of these structures. So what you need to do is you take one cell of your Sudoku and we represent it minimally with the 4 digits and 1 digit per neuron. So you have 4 neurons here and they will compete for being the neuron that is active. Because we know that only 1 digit can be there per cell. And then you build up more rules for the row rule, for the block rule, for the column rule, and then you wire it all up. And when you do that with a minimal representation, you only need 64 neurons and about 1,000 synapses for this children's Sudoku. But then again, we face the problem of the missing calibration or imperfect calibration and the trial-to-trial variations. So we do our in-the-loop training here as well on these motifs of winner-take-all structures. But here we need to play another trick because we want to have some recurrency so that once one cell is active, it will stay active, so it will have a self-excitation. And this is hard for artificial neural networks to model because it's time continuous and there is no time step. So what we did is we mapped this recurrent network to a two-layer feed-forward network and used the training rules simply for that. And you see on the left side a performance plot and before the training and right after the training. And the x-axis gives the fraction of the rates compared to the highest rate. And you see that, of course, when the rates are equal, so that you do not have a real winner, you cannot have a good accuracy. But if you are below that, then your winner-take-all structures really do the job, which is the highest frequency of input makes only this one neuron active. And this is how a raster plot looks like. Before the training, you see in green the correctly solved digits and in red the incorrect digits. And this is, for example, here in this slide here, in this slice, you see that the green neuron was active, which should not be the case, and the red could not compete. Here you have a time where this is okay, and here again you have some problems. And this is before training. When you do this after training with only the winner-take-all circuits trained, you can solve this Sudoku. So important to say that we did not train the network to solve Sudoku. What we trained is the individual circuits, and the problem is encoded in the connections. And by this, you could also connect differently and solve other kinds of these constraint satisfaction problems. And here again, this is the number of correct Sudokus as function of the number of empty cells, so to say the difficulty. And even after leaving out 8 of these 16 cells, the Sudokus are solved with 100% accuracy, which was not the case before training the individual WTA circuits. And also the time to first solution decreases. So left is without the training. You can see that sometimes it takes 1,000 milliseconds so that the network once was in this solution. And after training, you get your result after 200 milliseconds. Again, biological time divided by 10,000. So let's now come to my third and last example of experiments, which is neural sampling, or especially leaky integrate and fire sampling. And neural sampling is a way of a stochastic process where still every spike counts. So what you take as your variable is the spike times of your individual neurons, and then they are refractory for a specific time. And in that time, you denote the state. So if you have, for example, here, 2 neurons and 1 spiked, then you know that this is your 1-1 state because this other neuron was still in refractory. Then it leaves refractory. It's the state 0-1, and so on and so forth. So by this, you can encode binary states, and you need as many neurons as you need states. And when you wire this up, you see that it resembles a Boltzmann machine. And what you need is that these neurons are stochastic. Yeah, so you can do it mathematically with just stochastic neurons. But when you have a hardware implementation, you need to make these neurons also stochastic. So what you can simply do is apply a noise, an excitatory and inhibitory noise to each neuron, which is depicted on the left side. So you have your sampling neurons, you have some bias neurons, and you have these tiny squares here, which denote the noise terms. But this is not ideal for a hardware implementation because this noise maybe comes from outside, which is not what you want. So another method was developed, which was called sea of noise, where you have dedicated networks on the substrate, on the wafer, which do nothing but produce the noise. So at least you have it on wafer, where the bandwidth is much higher. And then you feed in these noise to all your different sampling neurons. So this helps you with saving the input bandwidth. And then we set up these restricted Boltzmann machines. So we have a visible layer where, for example, MNIST digits are displayed. We have a hidden layer and we have a label layer. And we can train this with a wake-sleep algorithm. So what you see here is a result of a simple network so that you can still see all states, once trained with a Poisson noise from the outside and once with a decorrelation network. And it started very bad, the agreement. This was done on purpose, so you can see the difference. And now we do this iteration, these in-the-loop iterations, and you can see that the agreement between the blue and the red distributions is already fairly good, and you basically see no difference between the Poisson noise and the noise from the decorrelation network. So now we are confident that we can train a network to do this task, and we choose two different data sets. One is the MNIST data set, and the other is a data set from the company Zalando called Fashion MNIST, because why not? And it shows you different kinds of clothes. So here we choose T-shirts, trousers, and sneakers. And they say it's just a replacement for MNIST. It has the same resolution, same kind of data format, so that it is a drop-in replacement for the MNIST data set. And in terms of classification accuracy, you can see on the left for MNIST and right for the Fashion MNIST, and we trained the classes 0147 and T-shirt, trouser, and sneaker. And the network was 400 sea of noise neurons, 200 sampling neurons, and in total 50,000 synapses. And you can see that after about 50 iterations, you get a fair classification accuracy. So these restricted Boltzmann machines, together with neural sampling, allow for more than just classification. For example, they allow for pattern completion. Pattern completion is the case where you do not show the full picture to the network, but you only show a part of the network, part of the picture to the network. So here we left out this lower right part, and you see that the network response, so what the visible layer does, is completing the pattern. And also the label response is, after a while, once it figured out in which mode it should be, is then the digit you would assume it should be. So this is something that your Boltzmann machine, your generative model, can do, which other classification networks cannot do. And of course, we can complete some clothes. So let's try to complete a T-shirt. And you see that this would, of course, benefit from some scaling. So we, of course, want to increase the resolution so that you can really see some nice shoes. But I think you can. At least the network knows what it sees. Yeah? So the label response is right in almost all the cases. So when it comes to generative models, they can, of course, dream. When you just let them run, they will traverse all the different modes. But here we wanted to try something different, which we call lucid dreaming. We want to tell it what to dream from. And by this, we clamp the label layer. And then, because of these backward connections, it will trickle down to the visible layer. And here, now we tell them to dream from digits. So we say, OK, please dream the number 0, and it will do so. And will also dream from all the other digits. And if you have some higher resolution, some other kind of data set, you could think about purposefully generating data which is just not present in your data set, just by saying, OK, please dream the number 4, or you could clamp multiple values and dream maybe from some kind of mixture. But this is work in progress. So you see here, dreams is 7. And dreams a 1. You can also see the hardware time in microseconds, so it can dream really fast. So let me summarize. So I showed you 3 different kinds of experiments on the BrainScale's wafer scale system, which is a spiking deep neural network that classifies MNIST. Winner-take-all units solve constraint satisfaction problems, and C of noise-driven restricted Boltzmann machines, they classify, they complete patterns, and they dream. And all these experiments rely on training the hardware in the loop, but of course we also want to investigate more on-chip learning, for example, that you can already see in the next generation prototype in the demos. And the accelerated dynamics, they really pay off for inference and generation. And last but not least, you are all very welcome to request access to our platform at the page neuromorphic.eu, where you can access the platform and play with our system yourself. Thank you.